So let's get back to Bitbake here. And so yeah, we're going to talk about how you build a specific recipe. Now, in a lot of situations, you'll see that the quick how-tos are essentially Bitbake and then the name of a recipe, and then magic occurs and away we go. Well, how exactly does that work? Well, basically, there's a search path that's put together by the various configuration files we have. When we say Bitbake and then the name of a recipe, we'll go and look at the manifest that it has constructed in memory of all the recipes that it's found, and then we'll basically run the appropriate set of steps based on the recipe that you've named. And we'll see in a second that you can in fact specify the specific version and revision, for instance, of the recipe that you want to run and so on as well, if you so wish. You can also run specific tasks from Bitbake by using the -c command. Now, Bitbake itself calls these commands, but in recipes we call them tasks, and that's just a historical thing. With Bitbake, originally they were called commands, but like I said, as a part of Open Embedded and the recipe system, they're called tasks. So task starts with a C, effectively, in this particular case. So Bitbake -c clean, and then my recipe will run the clean task on the recipe. This typically does the equivalent of a make clean on your source code. There's also what's called a clean all. This will do a make clean, but it will also clean up all of your any installed versions of the software that put into sysroots and that sort of thing as well. So if you will, clean all is kind of like doing a Mr. Proper, make Mr. Proper on the kernel, or make clean all, or very clean, similar ideas. And these are base tasks that are added to most recipes, depending on how what they're inherited from and that sort of thing. You can also get a list of any tasks that are available for a particular recipe by doing a Bitbake -c list tasks. This will list all the default tasks, as well as any tasks that have been brought in by the various BB classes that have been involved for that particular recipe. So there'll be slightly different tasks depending. We also can do, when it comes to recipes, you can also build one of various recipes that are made available. Quite often, there's more than one version of a recipe that's made available. Now, typically, it's the highest version that's built by default. So let's say you have a 1.0 and a 2.0 version of the recipe. It will build the 2.0 version of the recipe because it's the higher version number. That said, you can in fact change those values with things like what are called default preference or preferred version. In the case of default preference, you can actually set that as a piece of metadata in your recipe that will actually bump up your relevance. So by changing your default preference to a higher number, your affinity to being run will actually increase. Everyone's default preference is set to 0. If you set it to a 1, you will be built as the highest preferred version of a particular recipe, regardless of the version that's been made available. The other way of doing it is, if you've got 2 different versions, is you can actually specify the version that you prefer to have built in your local.conf file. And so you can, in fact, bend the rules again at your configuration level by specifying the version of a particular recipe you prefer to build. Now, why is it preferred? It's because what it essentially means is, if offered the option of this version or another, I want this specific one built. Okay, so again, it won't necessarily just build the latest. It will build a specific version if that version is available. If it's not, that's fine. It will build based on the other rules that are there. So when you say Bitbake my recipe, it will build the appropriate recipe. Again, highest version, the one with the highest default preference, or the preferred version in the reverse order I just said. So preferred version is built first. If that's not there, go with the highest default preference. Otherwise, the highest version is the order it's looked at. You can also specify a specific version you want built from the command line. Again, Bitbake my recipe dash and then the number itself. The the version number here is the version of the software you want built. So you'll see in a second we have a version and a revision. The version is the version of the source code that recipe is designed to build. Okay, so when you say my recipe 1.0, it means that you're building the 1.0 version of the source code that makes up my recipe. Okay, whereas you can have also revisions of a particular package. This tells you the revision of the metadata that you've written, and this is a -r and then a number at the end. And you'll find that there's several ways of incrementing this, but it's very typical generally to increment the revision of your recipe whenever you check it in, so that you have a way of referencing which revision of a particular recipe that you want to depend against, for instance. And again, you'll see that there is a -version, -revision number as a part of this. You can't just specify the revision without the version as well. You can also point it at a specific BB file. So you'll notice in all of these cases, there's no BB at the end. There's no extension. You can actually tell it to build a specific BB file, which isn't always typical to do, but let's say you're doing some testing and it can't be found in your path or whatever else. Generally, that means you've got a typo in one of your configuration files or something. It is possible to build a BB file directly. And for this case, you type bitbake -b and then the full path to where your .bb file is. And so you can specify the actual name of the file as opposed to the name of the recipe that you want built. Okay, so you can do that as well. Now that's not useful on term, but from a debugging perspective and so on, you can in fact run a specific recipe. Now, the next thing is, let's say you're building a really big image, and so especially on an underpowered machine, this can take a really long time. I know on when I'm building, for instance, on a laptop in a hotel when I used to do on a regular basis pre-pandemic, you might have really slow internet, and you may not have the fastest machine available to you. Maybe you're building a VM or whatnot. It can take a long time. It can take hours. I know doing a core image SATO on a lot of my earlier machines would take on the order of 3 hours, downloading, compiling, and so on, on a rotational drive and so on. And again, the more CPU, the more memory, the faster your storage, the faster it is. It's still on the order of tens of minutes, if not hours, for on a lot of machines, depending what it is you're building. The problem with this, of course, is that you will start your compile, and then, of course, you can either sit there watching your CPU get warm, or you can go do something else. And so it is not entirely atypical for people to start a build and then go to lunch or to go home for the day at the end of the day and whatnot to kick off a really big build. Now, of course, we all know what happens. Murphy's Law dictates that as soon as you kick off a really long build and walk away, of course, it will fail. And the problem with that, of course, is that let's say you had a 3-hour, in the scenario I had, let's say we had a 3-hour build ahead of us, and we start the build, we walk away, and it dies 10 minutes into the build. It means in the morning when you come in and fix the problem, we still have basically a 3-hour build ahead of us. And that means that we're not actually going to get any real work done until after lunch, and that's really frustrating. The thing to understand, though, is when it comes to dependency tree recipes, you start at that root, and then what happens is that your dependencies go out, and then they come back in again to build the final image. What this basically means is that there's a whole bunch of things happening more and more in parallel, and then less and less in parallel until we build the image that we're dealing with. In the case of just running Bitbake by itself, as soon as it hits an error, it stops. Okay, and so the first error hits, it stops, doesn't go any further. Generally, you want to see the error and so that you can fix it. However, if you pass in a -- continue or -k to Bitbake, it will continue. And what that means basically is it will go as far as it can through the build, regardless of that mistake, or rather that error stopping that particular path through the dependency tree. It will build the rest of the dependency tree as best as it can, as far as it can. And so in the scenario I gave with a 3-hour build, that dies 10 minutes into it. Normally with the dash continue, it might build for 2.5 hours before it finally can do no more. That means the next morning when you come in, you can see the error by rerunning Bitbake without the -k. You can fix the error, and then you might only have a half-hour build left. Okay, and that can make a really big difference. And so when you're doing an initial build, passing in the -k can solve a lot of those time problems. Okay, so it'll build as much as it possibly can. Again, you don't want to, when you're debugging, you don't want to use -k, but if you're just doing a bulk build, like I said, having it build as far as possible along that path will solve an awful lot of problems. There's a question here about optimizing build times. There's a number of mechanisms that can be used for that, things like the shared state and so on, which we're going to talk about in a second. The big problem with shared state, and for that matter, the more recent equivalency server and so on, is that you have to build it exactly the same way as what was originally built in the shared state cache. If you change anything, essentially, the shared state cache is no longer useful. So if you're building the same thing exactly the same way over and over again, shared state caches are great. And shared between teams across the internet or on a local network, super. However, as soon as you change a global configuration, at this point, you're rebuilding everything anyways. So they're only useful to an extent. If you've got a whole bunch of people that are doing exactly the same build, they're fabulous. If people are doing a whole bunch of other things, not so much. But as far as speeding up your builds, again, we're back to more memory, faster, and more CPUs. And because we're very I/O heavy, as has been mentioned, and in fact mentioned again here, the faster your hard drives are, the better. And again, building out of a RAM disk will always win. That's the absolutely the best way of doing it. If you can build on top of a flash-based drive, either SSDs will be marginally faster. They'll be about 10 times faster than a rotational drive. And then NVMe drive typically is more like 1,000 times faster, 100 to 1,000 times faster from an I/O perspective, which makes a really big difference. But like I said, even faster than that will be building out of a RAM disk. So the more RAM, the more you can tweak it to have fast storage, the faster it will be. So yeah. Stuck on installing these 2 packages in an image like 14 hours. Oh my gracious. The only thing I can think of there is that I mean, depending on how fast your CPU is, 14 hours is that's either an extremely big build, or it's you either have a CPU bound problem, a RAM bound problem, or an IO bound problem, or an incredibly large build. So yeah, depending on how many CPUs you have, 16 gig may not be enough. Oh, so probably your CPU is what's the CPU that you're using, and how many cores? Are you building on the Raspberry Pi? And what's the CPU on your laptop? How many cores do you have? Yeah. So the specific version and the generation of your CPU and how many CPUs you have available will make a big difference. I'm guessing that you might be only building on a single CPU, or maybe a couple of CPUs. 14 hours is an incredibly long time, especially for the Raspberry Pi. So in any case, so that's the deal with big dash continue. And the big thing to understand here is that when it comes to building things, when you're building a particular recipe, of course, remember we talked about all the different tasks that run: fetch, unpack, patch, configure, config, install, package, right? There's a whole bunch of different steps in there that are called tasks. When it comes to dependencies, what happens there is it will actually do the dependencies not based on the packages, but in fact based on the tasks itself. And so what it'll do is it'll build as far as it can. Rather, it will start dependent builds as quickly as it can before it's even finished building a particular recipe. So you'll find that, for instance, as soon as the development files that are available from a particular package are available for the next package to build, it will start building the next package, assuming that it has the CPU bandwidth to do so. So instead of building packages one after the other like this, it will actually build them in parallel somewhat. So as soon as it can start that dependent task, it will, which makes things a whole lot more interesting. So the thing to remember is that ultimately the dependencies are actually at the task level, not at the recipe level. There's also different ways of depending on recipes, which I believe we'll talk about later as well. And really what it all comes down to is, within reason, the more CPUs you throw at it, the better. A number of the maintainers have like 100 and, well, one maintainer in particular has 196 CPU server, and he can build Yocto Project, I think he said 2 or 3 times at the same time without running out of CPUs. But what I found is with 64 CPUs, you can actually get an awful lot done. But basically, the more that you can build against it, the better. So again, these are the default tasks that generally happen. Now, it's not always the same way, but these are the basic ones. Again, you have that fetcher stage first. This finds and downloads the source code via the various mirrors. If you are downloading things as a tarball, typically there's, of course, an unpack stage where it has to unpack and uncompress the source code appropriately. The patch stage, of course, is optional, but it allows you to add your own local patches to things. Again, patches are typically used to solve specific local things that you need to change, or security problems or whatnot. It's not intended as a replacement for upstreaming packages or patches rather, but you can. It becomes tedious to maintain patches after a while. But quite often there's things that you have to change specifically for your local way of doing things. Configure, of course, is the way of configuring a particular source code system, and quite often build systems do have a configuration stage in order to make things work appropriately. Compile is exactly what it sounds like, the equivalent of typing make. Install is what happens is that what comes out of your compile then gets installed into a temporary location from which it can then do 2 things. One is called populate sysroot. The other is building the specific packages that come out of it. Populating sysroot ultimately copies the development files that are a part of your build into the sysroot that is then used, pardon me, for dependent packages. The sysroot for your system is the user directory. So user lib, for instance, user include. There are per package sysroots that are built as a part of Yocto Project. And so if you have a dependency on a particular package, its development files will be copied into your sysroot before you are built. The idea is to have as small a sysroot as possible with only the things that you depend on in it, to make sure that all of your dependencies are accurately put together. You never want to have a build that builds differently on different machines just because of the number of CPUs you have. Building by accident is never a good idea. So by having per package sysroots, you make sure that you're guaranteeing that all of your dependencies are in fact listed, by making sure that a bespoke sysroot is always put together for that particular package. However, in parallel, it's packaged. Okay, so we build a package that goes into the package feed, and then separately we populate the appropriate sysroots for dependent packages to be built. Now, this is a normal set of, or rather a typical set of recipe tasks that you may find in a particular thing. It's not always the list. You can get a specific list of tasks by running the list tasks command to see how that works. And there's in fact more than what we listed here. These are sort of the most important of the list. Now, when you're running Bitbake, you will see that it tells you the number of tasks and which tasks you're on. It will also tell you which specific recipes being run, as well as the task that's currently running. Now, normally you will see this sort of bubbling at the bottom of your screen, showing you how many they're running. And there's usually one per CPU that you have at the bottom, and that will sort of change over time. But these are actually all going into what's called the cooker log. And so if you actually go and look in the your temp log directory, there'll be a cooker.log file there. This will actually show you all of the log steps, all the different things that are run. And you'll see, for instance, just for in this case, the hello VB file, you'll actually see that it does the fetch, unpack, patch, configure, populate, license, to pull the license out, compile, install, and so on. And you can actually see all those steps intermixed with all the other recipes that are built at the same time. Now, the shared state cache was brought up before. It is a way of solving specific problems and time-related problems, I should say. And to a large degree, it works the same way as a program like what's called C cache works for running C programs. Just as an example to describe how at the S state cache works, let's think just about C programs and how they work. CC cache essentially is a program that allows you to cache C programs. And if you think about a particular program being built, what are your inputs? The specific compiler that you're using, the parameters that are passed to that compiler, the specific source code and header files that are used for building it, and then ultimately your environment variables that are passed into the compiler. So those 4 or arguably 5 things essentially for whatever those inputs are, right? If you use exactly those same variables, the same environment, same code, same headers, same arguments, same compiler, the output should be identical, right? So if your inputs are the same, your output should be the same. What are your outputs from running a C compiler? Well, there's the object code that comes out the other end, or the executable for that matter, in case of building of the linking stage, and what comes out on your standard error, basically the text output from the compiler. And so what C cache will do, CC cache will do, is it will grab a copy of the object file and the output of the text output of the compiler and save it in its cache directory, such that the next time you build exactly the same thing, it will just copy the file from its cache and output the same text as if you ran the program as before. Again, it has to match the inputs exactly to get the same outputs exactly. However, the shared state cache does that at a larger level. It does this actually at the package level, the package data level, the package level, package write, RPM, license, sysroot, and so on. So the neat thing about this is that it will actually shortcut your steps. If the outputs of specific portions of your builds match exactly the way you've done it last time, it will just take the output of your prior time of doing it and just copy that into place. And you'll see this quite often when you're using a shared state cache from that somebody else has generated doing exactly the same build. Instead of going through the the fetch, unpack, patch, configure, whatever steps, it'll instead say populate sysroot. If you ever see that, it's actually downloading the or rather using the pre-built sysroot that was generated from the previous build and go from there. And we'll actually set things up appropriately. You'll find that the shared state cache is automatically turned on in any particular build. It's normally built as a part of your particular build directory. It is relatively common to move your shared state cache to a common location that is then shared between your builds, and it's entirely safe to share your shared state cache with more than one build at a time to make things easier. So like I said, shared state cache is on by default, and in order to share it between multiple people, it's just a matter of putting it on a shared drive that everybody can get to, or in the case of a shared state mirror, to put it to publish, let's say if you use an auto builder to publish its its shared state cache to somewhere where other people can see it, so they can then use it as a shared state cache to download those pre-built mechanisms that are there. Certainly when it comes to downloading, similarly, you'll find that the download directory that you build as a part of your build, it can also be published as a mirror or a pre-mirror if you want. But yes, shared state cache is absolutely something that can help speed things up. So just as an example here, if we, let's say we built hello, and then we did a bitbake -c clean hello, and then we rerun bitbake hello, you'll see that instead of rebuilding it as we did before, where we did the, the fetch, unpack, whatever, instead here, you'll see that it does a do populate sysroot set scene, do populate license set scene, package QA set scene, package write IPK set scene, and package data set scene. Whenever you see those set scenes, it's getting it from this shared state cache instead of actually doing the work longhand. And that's always a good thing, okay, if you can see that there. Some people don't always trust these kinds of caches. I can guarantee you that the mechanisms for making sure that a cached version of the output is predicated on the inputs being exactly the same. If the inputs are the same, the output should be exactly the same. This always works. Okay, it's entirely reliable. All right. That's not to say that people don't do overnight builders on build robots that don't use a shared state cache, to be absolutely certain. But when it comes to doing development and so on, your time is more important than making 100% sure all the time that it's the case. And again, we can be absolutely sure by using a CI build in order to make sure that that's the case. But for day-to-day things, you'll find that it's basically infallible. It will work exactly the way you expect. So I always say trust but verify. So let's look at recipes specifically. We're coming down towards the end of our particular time together. So let's make sure we get through these things here. So let's look at a recipe specifically. There's a number of different variables that you can set. We won't have time to go through absolutely all of them, but we put some key ones here into the slides here. The first one is the source URI. This has been mentioned several times. This is the universal resource indicator. And certainly what you add to it looks an awful lot like a URL, as was mentioned. The thing to remember is a URL is one form of URI. And typically what it has the protocol, a colon, and then the path, whatever it is you're looking for. People are used to URLs primarily in web browsers and so on. But like I said, a URL is a form of what's called a URI. And the way fetchers work essentially is the protocol used dictates which fetcher is going to be used. So GET or HTTP or whatever. And then, of course, the path tells it where to look for the rest of the information. There are some parameters that you can add after the source URI, source code URI that's provided, but you can also list patches and configuration fragments and other kinds of things as the list, which is your URI. Most variables in recipes are space delineated lists. So basically a big long string with spaces in between different things. We also have dependencies. Now we have both dependencies and R dependencies or runtime dependencies. Dependencies are build time dependencies. Okay, so if the other recipe has to be built before you because you depend on it at build time. Whereas an R depends is a runtime dependency. It means that the other recipe will be built and it will be installed on the target image because you need it at runtime, but it does not need to be built. You do not need it at build time, pardon me. Okay, so a runtime dependency does not infer a build time order. It just means that it needs to be on the target when you ultimately run. We also have various extra bits and pieces that allow you to modify how tasks work without directly modifying the tasks themselves. You can do that through things like extra OEconf, extra OEmake. These are anything you put into extra OEconf is automatically passed to the /configure in the configuration step. So you don't have to change the code for the configure task. Instead, you can just inject options to configure by changing that variable. Extra OE make, similarly, will add options to any situations where make is called on a regular basis through your recipe. Wherever you see the word extra something, typically you're adding to an existing thing that's there. You're modifying default behavior. So it's a way of injecting extra information without changing the code. You can also specify what you want to go onto a particular package by modifying the appropriate files underscore and then the package name of files. And so by providing a list of files or a globbed list of files with stars, you can specify what files go into which packages. So files underscore package name equals list all of your files, and those will go into that particular name package. So here's an example of ETH tool, for instance, and you'll see here that we have at the top the summary, the description, the homepage, the section. These are what's called descriptive metadata. These tell us a little bit about the information that's primarily there so we can extract that information later and to tell us what it does and where we got it from and so on. Not strictly required, just mostly for people looking at things later on, so we can get a list of what packages are there and so on. The section is a part of the packaging mechanism and tells you roughly what the category of the package is. It's only relevant for certain packaging systems, but it's a good idea to include. We then have the license. You'll see that we have the license as a string that's understood by humans, and then we have the location of that license. And indeed, we can specify the files, both the files where it can be found or the portion of the file where it can be found. You'll see that we specify a license file, but we also specify the lines between line 4 and line 17 of a particular C file. So at the top header and an accompanying MD5 sum. Now, there's actually MD5 sum and SHA-256 sums that have now replaced it. The point is there is a hashed number that allows you to indicate that, but this was the hash value of this particular file at the time that this particular recipe was written. It means that if it hashes that file again and gets a different MD5 or SHA-256 sum, that in fact it will fail your build at that particular point in time. It means that it has changed since the recipe was written. And so this isn't so much a cryptographic way of making sure that nothing's been tampered with. It's a matter of making sure that the recipe hasn't changed from what, pardon me, the license hasn't changed from when this recipe was written, is what it comes down to. And you'll see that the inference in this particular case is that the GPL v2 plus recipe or license, pardon me, is specified in these two locations. A separate file, and then in at least one of the C files or header files. If it's in every single file, you typically choose a central header file or your main.c file, whichever that is, and you list that, basically the most important location of the license in your source code. Again, the idea is to make sure that it doesn't change from when the recipe was originally written. Next, you'll see we have our source URI, and so here we have the full path to the source code. You'll notice we have a $ and then PV in here in curly braces. This ultimately indicates the package version, and it's inferred by the name of the recipe itself, because the name of the recipe is ethtool underscore, not a dash, but an underscore 3.15. This becomes our package version, which ultimately is replaced here. So this is ultimately downloading ethtool 3.15.tar.gz. Okay, now you'll notice there's also a kernel org mirror. There's actually several mirrors for GNU and kernel and so on. The problem with a lot of build systems like this, especially automated ones, is that they quite often run at specific times around the world. For some reason, a lot of people like to run CI builds at 2 a.m. wherever they happen to be, and it meant that there was specific load on specific servers around the world, which could cause problems. And so there's a number of Open Embedded and Yocto Project maintained mirrors, so that you will go to a random mirror to download the source code to try and spread the load out so that no one server is hammered at any particular point in time. Otherwise, Yocto project builds start becoming essentially a denial of service, a distributed denial of service kind of attack otherwise. So that's maintained. You'll notice under it, we have a number of local files that are found via the BB path in your system here. So file : // these are files that are in your recipe directory itself. You'll see there's a couple of patches and a p-test script and so on and so forth for running testing on the target and that sort of thing. Next, you'll see we have source URI, MD5 sum, and SHA-256 sums. Now, the MD5 sums are deprecated. You don't need to specify those anymore. But we have the ability to, in this case, since it's a tar file, we are specifying the SHA-256 sum of that tar file for a couple of reasons. The first is we want to make sure that at the time of writing a recipe, this was the SHA-256 sum of that particular tar file. So again, we want to make sure that that source code hasn't changed for a number of reasons. It means that the author hasn't changed the file, which is a cardinal sin. You'd never want to upload a version of a tar file and then change it in the future. That'd be very bad. So you want to make sure that the author hasn't changed it. You also want to make sure that an attacker, some sort of hacker, hasn't changed the source code from before, that it is in fact the source code that was intended by the recipe author in the first place. Or for that matter, in the case of downloading the source code, it may not have been downloaded over HTTPS. These days, almost everything's downloaded over an encrypted connection. But in the past, a lot of things were passed over HTTP only, not encrypted. And so source code injection could happen, unfortunately. So the idea there, again, was making sure that the SHA-256 sum guaranteed that the source code was not modified in transit from the server to you as well. So it's trying to solve a number of problems. The big thing is the source code that you download is the same as the author of the recipe in the first place. And that's the problem that you're trying to deal with. So this is what's called an attribute. And so the source URI attribute specified by itself like this applies to the basically the first thing in the list, which conventionally is the tarball or the actual source code itself. If you have more than one thing that you're downloading, you can actually apply a name to each thing, and then you would actually have an attribute for each thing. So there'd be a file dot whatever SHA-256 sum attribute per thing. And it starts getting a lot more complicated. But ultimately, when you specify it this way, you're specifying it. The idea is you're specifying it for this. You actually can put a semicolon and SHA-256 sum blah, 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 blah at the end of the file if you want. It gets messy. So having this separate attribute allows you to specify it on a different line. And you'll find that if you don't specify a SHA-256 sum, it will actually complain, and the error message will in fact include the appropriate line that you need to add to your recipe. And so you can just cut and paste it directly into your recipe itself. So the build will fail. Actually, hold on. Yes, I believe the build will. Does the build fail? If you don't have a SHA-256 sum, I believe it does not fail. It just tells you the message. But yes, if the SHA-256 sum is wrong, it will fail. Yeah. Typically, it's correct, and so it doesn't. But you'll find that when it comes to SHA-256 for either the license or for the source code, if there is a mismatch, whether or not it continues in the case of not having a correct value, it will tell you what the value should be. And if you're expecting it to be wrong, you can cut and paste it into your recipe. If you're not expecting it to be wrong, be very careful, because at that point, something bad may have happened. You need to investigate why it didn't match at that point. But if you're just being lazy, and by lazy I mean being efficient with your time, and you don't actually have the proper SHA-256 sum for something, best practices is to just not include it and then take the error message as the value. Of course, you do need to verify that it is in fact the same as what you downloaded, but In the case of generating a SHA-256 sum for a file, it's very straightforward to do that from the command line. There's a utility called SHA-256 sum, similar to MD5 sum. But for a portion of a file like we do for licenses, getting a partial MD5 sum from a part of a file is not something we can easily do. And so in this case, you pretty much have to take the error message to get the appropriate value that it's expecting. You'll notice next we have our inherits here. So inherit, and you can do it as multiple lines or a single line. This will look for autotools.bb class and ptest.bb class. And again, they are effectively included at this location. Again, think of them still as being objects, classes that you're inheriting from. So this is effectively multiple inheritance. Next, you see we have an rdepends here for a particular package name, specifically for p-testing. And so this takes the package name of the whole file, which is ethtool. So this will actually expand to rdepends ethtool-ptest. And we'll see what these operators mean, but it's actually adding make to that list to the runtime dependencies. So we're saying we want make on the target in the case of ethtool ptest. So what can a recipe do? Well, it basically can build whatever you want from source code, host tools, compilers, utilities, the bootloader, kernel, libraries, interpreters, user space applications, whatever it is you are building, images. Basically, a recipe will take a bunch of inputs and give you the output that you're looking for. And so it's basically how to go from one thing to another. Okay, so everything that you run through Bitbake is a recipe, or it's a piece of metadata that modifies a recipe that you have together. Again, there's package groups that can be built as well. There's also full system images, there's SDKs, there's all sorts of things that you can build as a part of a recipe. But let's go through the operators. Now, there's a big long list of operators, but it's always good to go through these things. And it's because essentially it's not always obvious how these work. If people are used to the various utilities and languages that these things come from, it's very straightforward. But if you're not, these things can be a little bit confusing. The first thing to remember is that this kind of works like, although it's written in Python, it kind of works like a makefile. It kind of works like Perl. It kind of works like a few other things, and there's a few new invented things as well. Okay. I know it sounds weird that Perl was used, but the dot equals is originally an operator from Perl. But the thing to remember is that when we assign variables, it's what's called a late assignment. So like in makefiles, we don't actually do an actual assignment until we first use it. Okay, so this is why it's called a late assignment. What this essentially means is that we don't actually use that value until we first dereference that variable. So when we say a equals foo, we are in fact making a promise to set a to foo the first time we dereference a. Let's contrast that to the bottom one here, which is an immediate assignment. By saying d colon equals x, y, z, that means we are doing an immediate. D is immediately becoming that, regardless of us not dereferencing it. Okay, so they have slightly different meanings, and the order of the operators is a bit different. Whereas the immediate happens now, the a equals foo will happen in the future. Okay, and in fact, in this particular example, a wouldn't ultimately be dealt with until actually quite a bit further on. Next is we have b question mark equals. This is what's called the default value. This is setting b to 0t. In the case of b not having a value otherwise. And the idea here with b is it will take the first default. Okay, so if b is not set at this point, okay, b does not have a value, a promise, if you will, set already, it will be set to 0t. If there's an assignment thereafter of b equals, for instance, it will override the default. Okay. But it's always the first default value that ultimately takes. If you set another default later on, of course, it will not be valid. Okay, so it's the first default value that's set, because the question is always, is there a value of b set? No, okay, this is the default. right? So the next time round, it'll say, is there a value of B? There is. Okay, let's keep going. All right. However, we also have what's called a late default. Okay, question mark equals. That's a double question mark. And this essentially sets a default at the end of time. Okay, so before we use anything, if C has not been set at the very, very end, this will be taken. However, with a late default, it's the last default value that's set. So it's the first default or the last late default. Late defaults are overwritten by defaults. And so we have different levels of defaults, if you will. So if you were setting a default globally, you probably want to, and you want it to be easily overridden, pardon me, you can use a default value. However, if you're trying to set a default in a recipe in such a way that other people can override it either in configuration or ultimately in the recipe, setting a late default is quite often a better option. And again, it just depends on exactly what you're trying to do and how you're trying to do it. But it means we have multiple ways of making sure that defaults can be set at different levels and still be overridden at the appropriate time otherwise. Okay, so if nothing else is set, the last late default is taken. If not assigned, the first default will be taken. Otherwise, of course, assignments are work the way you'd expect. Other than late assignments happen the first time the variable is dereferenced, and immediate assignments happen the way you would expect in other languages. We can also append to things. Now we can do a dot equals to append to a file. You'll notice that if we start with A being foo, if we do an A dot equals bar, we'll get foo bar. Okay, there's no implicit space when we append. We can also do what's called a prepend by doing an equals dot. This is a made up operator for Bitbake. Here we have a W0. If we prepend to that, if we take B, which is 0T, and we prepend to W0, you'll see that of course you'll get a W00T. So again, prepend with no intervening space. Plus equals works what looks like make. Okay, so this will do an append, but with an implicit space. And so up here, C is ABC, and we're doing a plus equals, and so it'll be ABC, D, E, F. Okay. Down here, you'll see we have a D equals plus UBW, and so you'll see that, of course, this is UBW space XYZ, right, based on these values up here. Yes, it's autocorrect. I noticed that too. I have to fix that at the end. But yeah, it helpfully did turn my 0 into an O. Yes, good eye. I had noticed that myself. Next you have here is more recipe operators. In this case, we have what used to be underscore append. So you'll see in older, certainly in books and older examples, we'll have an underscore append. This is a different way of doing an append. And it's like doing a dot equals, except that it happens at a different time. Whereas all the things on the preceding page happen in order, and they happen in line with the other operator we're talking about, these are kind of post operators. These are operators that happen at the end of time before we use them. And so whatever happens before now happens before now, whatever the outcome of that is, we're saying we want to append to that. So let's say we have an A equals foo like before, and then we do an A colon append equals bar. What that means is whatever happens to A with all the various normal operators, at the end of time before we use it, we're going to append bar to whatever that value happens to be. So A equals foo, append bar, we get foo bar. Okay. If we had the dot equals before, right, it would be foo, and then A dot equals bar, and then A colon append bar, it would end up as foo bar bar. That's just the way it would work. All right, but in this, if this is the only values that are there, it will take whatever A ultimately has become and add a bar to it. Same thing here, and you'll notice exactly the same typo here with an O. B equals 0T. If you do a prepend colon prepend, it will add W0. And again, we'll get W00T. However, in recent versions, the last couple of versions of Yocto Project, what's also been added is a remove that's very handy. This will allow you to do exactly the opposite and remove values from a particular variable. In this case, we do an A:remove, and remove OOB from A. Since it was foobar before, it will turn into far, for instance. Okay. Same with remove B remove 00. Of course, we'll get WT out of that. And so there's it allows you to either build things up or tear things down appropriately. This was something we couldn't easily do before without messing around with Python directly, which was a little bit annoying. And so instead, being able to do that with the colon remove is much more useful. We also have various what are called override operators. And so what this allows us to do is specify different overrides that can be set appropriately. Now, you would set them to whatever makes sense at the time. In this case, the example we've given is OS, Arch, and machine. Normally, you would specify things like Linux and ARM and whatever. But these are ultimately what are called overrides, and they allow you to change what happens based on whether or not they're set. So in the case of OS being set as it is here in the overrides, when we say A:OS equals ABC, we would override the value of A to ABC because OS is set. Okay, so although we set A equals ABC in lowercase, because the override OS is set, this would instead be used. This would override this value. Okay, so A in fact would be set to all in caps ABC because OS is set as an override. And by the way, overrides are read left to right. And notice down here we have an A append arch. Okay, so this basically is a conditional append. Because arch is set, in fact, we would then append to A, and so A would become all in caps ABC, and then DEF in lowercase. We also have a conditional prepend, and of course you can do A prepend OS. Again, OS is an override that's set, and so we would have all in caps X, Y, Z, ABC, all in caps, and then DEF lowercase in this particular situation. Now, it is in fact possible to reverse these two things and have OS colon prepend, but those changes the meaning. Okay, so the having the override at the end applies to everything before it. So by swapping these two around, in fact, it would change the meaning of how it works. All right, so this is the order you typically want to see it in. A append and then arch. The order matters. You can also unset variables, okay? And so again, this isn't something you always want to do, but again, because you can change anything, it's important that you can then undo certain things. So let's say a recipe sets a particular variable, maybe you want to delete that variable for whatever reason, you can call unset, and that works for variables, that works also for attributes and other things like that, okay? So you can, in this case, it's a task attribute that we're unsetting. So you don't have to set it to null. In fact, you can unset it altogether. Oh, Gravestone says, I'm assuming you're talking about remove. I didn't see your comment, sorry. Does the remove all occurrences or just the first? It removes all occurrences. So yeah, it will not only remove the first, it will remove all. Bitbake variables, there are many different ones, and again, we don't have time to go through all of them, but there are several that are worth talking about. The first one is what are called automatic variables, and there are three in particular that are worth mentioning. The first one is topdir. This is the name of your build directory, so the directory from which you run Bitbake. When you run OE. What's it called? Build the net OE to build a build directory. It will create a directory inside which there's a temp directory. That top level directory is called topdir, and it's from where you run Bitbake and all those things. There's also a series of layers that are put together as part of your build in your BB layers file. And layerdir will expand to whatever layer your file currently is in. So if you write a recipe and you reference layerdir, it will expand to the full path to the layer that you're currently in, which is very handy. And then finally, $file will in fact expand to the file name, the full path to the file name you're in. And so you can get a lot of information from that as well. And so those three things are always set. Can you override them? You absolutely can. Should you? No, you shouldn't, because these are set appropriately. Their meanings shouldn't be changed. So so just to go back to Gravestone's question there. So I believe it would only remove the 0T in the middle. I'd have to double check that, but as far as I know, it will not do nested ones. I believe it's the first. I'd have to double check that. If you're starting to do things that are that complicated, you probably made another mistake. So yeah, no, I don't believe it. I don't believe it'll do nested. But again, I've never had to do something that complicated with it, so I'd have to go double check. The next thing is policy variables. Now, these are the kinds of things that you'll see typically in your distribution, and well, actually, for that matter, your BSP layer. But the build architecture and the target architecture are important. The build architecture, of course, by default is guessed based on the machine that you're on. It will basically do a uname and figure out the machine that you're currently on. You can force it to something if you want, but typically it's the machine that you're running the build upon. The next is the target architecture. Now, the target architecture is a part of your BSP. You're building for an ARM target. You know, you want to know what to cross compile for. And so that will be the next thing that's there. There's a lot of other things as well, but those are the two big ones. And again, we're quite often cross-compiling from something like x86 64 to, let's say, I don't know, AR64, for instance, or whatnot. Although, as we get more and more 64-bit ARM build systems, we may well be building on AR64 for something else, maybe RISC-V. Like I said, those are not necessarily the same architecture. We also have various build time metadata. We have things like the package name. And again, this is derived from the name of the recipe file itself. We also have what's called the package version. Now that can be explicitly set. It can also be derived from the name of the file itself. Again, it's the first number in the file name. It's the package name _ version _ revision. Okay, PR being the package release. Okay, or R0 in this case is the default. After that, we have P and PF. P defaults to PN-PV. Now, the file name itself will be name _ version, but the P will be package name -PV. The thing to remember is that the name of the recipe always uses underscores. Everything else uses dashes, and that's an inconsistency, unfortunately, in the way it was put together. There are reasons for it. Just remember that when you're naming a BB file with underscores, but for everything else, including the various directories that we build, it's always a dash, and it's a very common mistake to exchange a dash for an underscore or vice versa. Just bear in mind that there's consequences to getting those wrong. Okay, so again, recipe file names have underscores, everything else uses dashes. Okay, and PF you'll see is PN, PV, PR, okay, which is that revision, that R0 or whatever. Jesus is saying, what best practices do you recommend to keep clean and maintainable recipe? Following convention, putting things in the canonical order, making sure that you keep things simple, that you follow the coding standards for recipes. No extra spaces, that you align things appropriately. We don't get into that much in this particular class. It's described in the multi-date classes that we do. It's also in the documentation for Yocto Project. But the idea essentially is to look at the recipes. They're all generally consistently written. in such a way that it's hard to tell who wrote what, and that's because there's a coding standard to follow and a canonical order in which to put things. We also have the file dir name. This tells us the directory name inside which file can be found. It will automatically strip off the actual name of the file and give you the directory you're in. There's also something called the files path, and this is the path in where things can be found. You'll notice that it's now this has changed over time, but it basically will look in file dir pf, p, pn, and files, and it will make sure that the, for instance, when it's looking for a particular include file, that it will look in these locations, and you'll see that it'll actually look in specifically named directories based on the version and revision, so that you can optionally include an include file based on the version and whatnot to make things easier. Build time metadata, of course, you've got that top dir build directory, the temp dir. These are typically things that are set as a part of your local.conf or your specific recipe automatically. Temp dir is where all of your temporary files go, and it's in your top dir. As you can see, you've also got what's called your working directory or work dir. This is under temp dir work, and then your pf. So basically each thing is built there. You've got your source directory, your S directory, which is work dir p. You've got your build directory, which is defaults to S, but if you want to build out of tree, you can actually give a separate directory for that. Many recipes do. We also what's called the destination directory, or D. This ultimately gives us the location where we are going to install our files before they're made into packages. It's your desk directory. So it's basically a stopover point before you are packaged. We also have what's called the deploy directory, which is the temp dir deploy directory where images and other things live. And of course, the deploy dir image directory is under the deploy dir. And again, that's that images directory. And so you can see all of these are overridden. One of the tricks, if you've got an SSD or a RAM disk or whatever, is you can actually set your temp dir to point to that fast storage in order to make things faster. So even though your build directory is somewhere, because everything under temp is literally temporary, you can actually move it to fast storage somewhere. So you don't even have to put your build directory on your NVMe drive. You can just point your temp directory there appropriately. And that doesn't mean pointing to /temp, it means pointing it to a specific location where it's built. But nothing in the /temp directory needs to be kept. It will be recreated minimally from your shared state cache. If you delete it and rebuild it, it will rebuild faster and smaller, because of course it doesn't need to do all the source code changes. It doesn't have to rerun the compile. It just downloads the results from the shared state cache. Again, lots of different dependency metadata. We have things like depends and provides. Depends, of course, gives us a list of build time dependencies. Provides is what build time dependencies you provide to others, and you'll notice that it's your P, which is your package name and version, your PF, which is your package version and revision, and your PN, which is just your package name. It means that people will depend on just your package name or a version of your source code, of your package rather. And so you have a very tight way of depending on a particular kind of package that you want. We also have a series of runtime dependencies, things like rdepends, which are runtime dependencies, rrecommends, which are recommended packages. Now, these are dependencies that are optional, if you will. So if available, a recommended runtime package will be installed on your image. However, in the case of suggests, this is primarily for files to be added to the suggests line of your package. This is generally more useful for Debian packages than anything else. We also have rprovides. So this allows you to specify what runtime names you provide for others to rdepends upon. You can also do what's called an R conflicts and an R replaces. In the case of the conflicts, you're basically saying that you conflict with a different runtime dependency. Typically, if you have more than one way to provide a particular runtime dependency, if one conflicts with the other, you do an R conflicts with the other package, meaning that they both can't be installed at the same time, which will give you an error. However, if you also provide what's called an R replaces, you can basically both conflict and replace somebody else, and that will mean the conflict means only one of you can be installed, and replaces means essentially I replace the other person, and that second, the one that's marked as replaces, will ultimately be installed instead. And so you can essentially mess with dependencies and both runtime and build dependencies appropriately as a result. So also common metadata. So this is our descriptive metadata that we're dealing with. The summary tells us the short one-liner as to what a package does. The description, on the other hand, although not in the list here, gives you the long form version of the description. The homepage, there's actually homepage and bug tracker and a few other things, author and so on, that you can specify. These tell us where the information came from, and other information like that. The license gives you a list of licenses that are relevant to the source code you're dealing with, whereas the lick files checksum ultimately lists checksums for all the different files that contain the licenses and so on. And again, that's just so you can see what they are, and so that the licenses can ultimately go into the manifest file that we get as a part of the build. Source URI, of course, specifies where the source code comes from and all the patches and configuration things and other bits and pieces required in order to build the package. And then, of course, the files variable specifies what goes into each one of the packages. And again, it's always files underscore something. But let's look at some other examples so we can see how these fit together. But really fast, let's quickly look at some other questions here. As far as I understand, the Yocto way, inherit, include, require as much as possible. Yes, again, it's not so much the Yocto way. It's don't repeat yourself. You're trying to keep your code as clean as possible. Reuse is always the better way to go. Just set things that explicit needs to be set. Always keep it default. Yes, I think you're saying basically only set the things you need to set, otherwise rely on defaults, and that's correct. One version recipe for every version. Don't override older recipes. Make a new version. So one recipe per version can be done. You can actually put more than one recipe, more than one version into a single recipe. It's harder and more difficult to maintain. It's possible, but yeah, generally it's one per file. And again, what you can do is you can include an older and make changes for a different one. You can also rewrite a recipe to be a common include file and then include that into the various versioned recipes. There's a few ways of doing it, but the idea is to try to reuse as much as you possibly can. And then the big thing is that if a layer needs to make a specific change to a recipe, of course, you can use BB appends and other things to modify a recipe from a different layer. That's what it comes down to. Always try to extend or include a different recipe instead of rewriting it is what it comes down to. It's possible to export one Bitbake variable from one recipe to make available from inside another recipe. As far as the recipe is concerned, no, not typically. Nor would you want to, because that provides a different layer of dependencies that's problematic. At that point, you want to make changes in your local.conf or in one of the other configuration files. These things are always provided via policy in the distribution layer, through overrides provided in places like the BSP layer, or in settings in your local.conf file. You don't typically want to have a variable in one recipe modify another recipe. That would cause problems. So yeah, you don't tend to do that. Is it strictly possible? Anything is possible. Is it a good idea? No, it is not. If you look at the lower right-hand corner of every slide, there is a link that will take you to these slides. So yes, it's been shared from the beginning of this talk. We split, and this is a recording that will be on YouTube as well. We split our software packages. We ship into packages on different layers. The BSP is the third layer we use. Yes, and you can use an arbitrary layer. It's a list of layers. It doesn't have to be 3. It can be a lot more than that. Well, like I said, let's look at a different recipe. Let's look at BC. And so you'll see that this uses things like lick files, license files, checksum, and source URI. So here's our descriptive metadata up here, right? Summary of the homepage. Here's the license and license file checksums. You'll notice this gets into a lot more detail as to where they come from, different header files and other kinds of things. The section and the depends here are next. You'll see this is where the source code, this is packaging information. You'll see here we have our source URI and information, so our MD5 and SHA-256 sums, our source code where it comes from, a patch, right? You'll notice that we have this on multiple lines. You'll notice that from a coding perspective, it's space equals space. There's no extra information here. However, in the case of source URI, there's a whole bunch of spaces here that line up the things that come in. So it's typically 1 per line, again, lined up, just like we've shown you, of course, the backslash at the end to wrap the line and so on, just like you would do in Python. Here's our inherits next. And then here we have what are called alternatives. This basically tells you, in this particular case, an alternative for BC is DC. These are things we haven't talked about yet. These are other variables that allow you to specify things appropriately in the recipes. Again, there's a lot of variables that can be set. This is the canonical order, otherwise, though. Descriptive metadata, licensing, packaging, source code, inherits, and then our overrides happen after that. It's actually overrides, packaging, and then extends at the very end. As far as building upon BB classes are concerned, again, inheritance as much as possible. Whenever you're building the same sort of recipes over and over and over again, if they can be generalized into a class, you can, of course, add that as a BB class to your layer. And it means that other things can then inherit from it. So again, if you see the same design pattern repeatedly, building a BB class is a really good way of doing things. The BB path will point to each one of the layers. Under each layer, there's a classes directory. You just put it into the classes directory and it will be found by the inherit. Next, we have FLAC as an example. And so this is going to show us inheriting from both AutoTools and getText, and it's going to play with extra OEConf and a few other things, just showing you what it looks like. So again, here we have our descriptive metadata up here. Summary, description, homepage, bug tracker. We have our packaging information, in this case, the section that it's going to be in as far as packaging is concerned. Again, not really important for things like RPM, but IPK and Dev use this. Here's our license and checksums. And so you'll see that we have a list of all the licenses that are relevant, the locations where they can be found. It depends on libOg. Okay, so let's say, in this case, FLAC uses the OG library. So we can find where the source code is, right? And then here we have the source URI checksums. You'll see here that we actually specify the CVE product. So essentially what product to look up on the CVE list. Inherit AutoTools and getText. This allows us, again, to inherit from those 2 different BB classes. Now, part of AutoTools, of course, is there's a configure step that runs /configure. Instead of rewriting that code, we can inject extra information that's passed into /configure by specifying an extra OEConf that will be passed in the configure step. And you'll see we actually have some dynamic metadata here. Whenever we have a $open curly brace @ sign, what's in there is in fact interpreted as Python code. And in this particular case, it's basically trying to say, if the tune features variable includes AltVec, we want to pass in, we want this variable to be added. We want extra OEConf to have enable AltVec added to it. Otherwise, disable AltVec. Same with Core 2, Core i7, this enable SSE or whatever. And so you'll see that we actually have the ability of adding extra information to OEConf depending on the value of specific variables, which is pretty interesting. Here we can specify the extra packages that we want added to the list. So by default, it uses the package name -docs and whatever. In this case, we're adding specifically named packages to the package list so that we can then add what files are added to each package. And again, you'll see we have a bunch of blobbed files here added to the various package names that are here at the end. The PN, of course, expands to FLAC, whereas all these others, of course, are named explicitly. Let's see now here, another question. How can I point to a specific Git tag in my recipe? The source rev is a good one. For example, source rev equals yes. So you can, in fact, do that. The other way of doing it is you can specify the source revision in the URI itself. There's an attribute that can be passed to that to make it work appropriately. So next we have grouping local metadata. Again, if you've got common metadata that you have on a regular basis, we can either include or we can require specific files. Again, in the case of include, it will look for it, and if it doesn't find it, it doesn't error out. However, if you require, if it does not find the file, you will actually get an error. Okay, so as I mentioned a couple of times. Let's look at a different example here. In this case, we'll look at Ophono. And again, you'll find it under Pucky Meta Recipes Connectivity. And in this case, the idea is that it has an INC file that can then be used by other things. You'll see that it includes a number of different pieces of metadata. It also actually changes one of its tasks. All tasks start with do and then the name of the task, install. In this case, we are actually appending to that particular thing. And actually, I think it's actually :append these days, in fact, in this particular case. And so here you'll see we have require ophono.inc, right? And you'll see that, so it'll pull in that inc file, but otherwise it overrides a few things. Here's where the source URI is, source URI, and it sets the C flags. You'll see we actually do an append on lib. In the case of the override libc, UC libc, this is actually an older recipe, so it's using the underscores instead of the colons. These should be colons, generally speaking. But otherwise, this would add this in the case of UC libc being used. But otherwise, the inc file would look like this. We have our descriptive metadata at the top, our inherits. Here we have our dependencies. Now, strictly speaking, these two lines should be the opposite way around. Dependency should be before inherits, but whatever, it's fine. We have now these variables are used primarily because we are. You'll see that we're actually including system D here. We're inheriting from system D. There's a couple of variables that it uses, things like the init script name, for instance, and so on. This one actually params is used as part of update RCD. But otherwise, we have our package configuration again with some dynamic metadata, and then we have package configuration information that is added again depending on what things are set appropriately, whether we've got Bluetooth enabled or whatnot. Here we have our extra OEConf that's passed in for configuration. Again, system D settings, in this particular case, what the name of the service file is. We are adding to the install step, we're adding some extra steps, again, without actually rewriting the install step. We're just saying append this to the do install. And then again, we have our packaging and runtime dependencies here at the bottom. And again, more packaging information here. Okay, I'm going to suggest perhaps that we stop there. we have a couple of we're never quite sure whether we're going to start this chapter or the next chapter when it comes to the second session, but effectively this is probably where we'll stop for today. Well, for this session, I should say, not today. We will pick up from here in the next section, which will be in 1 hour, according to the schedule, and we should be able to go from there. But we'll start with when things go wrong, and then we'll go to image building. Yeah. Well, let's just let's see here. Okay. So let's see out here. It seems like there is a question as to whether or not we'll be able to do this extra chapter in the afternoon or not. So let's just quickly keep on going here, and we'll just try to get through this next chapter quickly enough so we can start the next chapter, I guess, then instead. So let's quickly talk when things go wrong then, and then we'll take our break. Sorry. So the first thing is that when things do break, you're going to find there's a couple of different ways things can break. The first one is syntactically, if it breaks. And in the case of syntactic break, it's the Python will complain. Basically, it's a syntactic problem. Bitbake doesn't understand your metadata. You just have to solve those. If Bitbake doesn't understand your recipe, it's never going to work. However, for logical errors, ones where things are wrong, you sometimes want to see what your variables are set to. And for that, you can basically do that by looking at what the output are for all of your various things, for your description, source URI license, and so on. And so if you want to see, for instance, what is your S actually set to, right? What is workdir? What's it set to? What you can do is you can run bitbake -e and the name of the recipe, and that will actually dump out all of your metadata. And there's a lot of it because all the dynamic metadata and everything else runs as well. And so if you basically do this, and let's say you do a bitbake -e and then the name of a package, and then you use grep to look for the name of your variable, of course, it will output the exact thing that you're looking for, so you can see what they're set to. So you can either grep it, put it into less, whatever, look for the thing that you're looking for. So here's bitbake -e netbase, and you'll see that it'll show you the full path to your particular file. Okay, so same sort of thing here. Let's say you want to see your PF, right, for netbase, or you want to see what your build directory is, right, with your git commit message and everything, what the name of your packages are. You can basically see whatever your metadata happens to be by grepping information from your bitbake -e. You can also see all the steps that were taken by looking at your cooker log. And so if you look under your temp log cooker, there's a couple of extra layers there, but ultimately it'll give you the name of the log file that you want to look at. And of course, it will show you all the different steps that happen at that point. Now, each one of those actually leads to its own log file. And those are actually kept in your work directory. You'll find that there's a directory under your work directory called your temp directory. Unfortunately, there's TMP and there's TEMP. Your TMP directory is the global temp directory for your build. The TEMP directory is in your working directory. It's referred to by the T variable, and it is where your logs are kept for your individual tasks. And if you look at those, you'll see that we have a series of files under under TEMP rather, that start with the word log, and the names after them specify the task therefore. And in fact, you'll see that there's in fact task, there's actually a dot number at the end of most of those files, but there's always a symbolic link to the most recent one. The reason why is because every time a system runs, the PID, the process ID of the task that was running at the time is appended to the name of the file, so it doesn't overwrite any logs that you've had previously. But again, these default names will always symbolically link back to the most recent version of those log files. And when you see an error, a logic error, it will actually point you to the specific log file, to the full path to that log file, telling you which one to look in. Similarly, there'll be run files. These actually will specify the steps that actually generated the log file itself. Okay, and so typically the tasks have a set of shell commands or whatnot. Those are all specified in the run files.